I like to study Mars. We'll get into that in a little bit about how that came to be. But yeah, I was in the prior service military, got out, went to ACC, and then went on to Jackson School of Geosciences, where I'm now studying Mars. Primarily, I'm a geophysicist, right? I'm a planetary geophysicist, and my primary tool that I use is numerical methods. I use numerical models to model physics-based equations. Here, we'll go into what this is later. It's an advective current in a cratering flow field. And I want to put this caveat out there. There's all types of modelers. There's the people who do like geomorph and things like that. I don't try to recreate any one setup. I don't try to recreate Mars in my computer. I say what range of like values are reasonable, and that's how I use modeling. And inside that model, I use remote situ data. It might be, I use a lot of MOLA topography, which is the topography of Mars, but there's mineral maps that might tell you something about how water moved on Mars, so I might use those. So I do a lot of ArcGIS. And then I have an entire like side project PhD going about, I've told Pete all about it. I've been writing about it a lot lately. And it's fluid dynamics, and it was trying to understand whether my governing equation was going to break when I did this, and it's kind of like morphed into its own thing. Planetary, though, I want to focus on that word because we're not geologists, which is good in here because I irritate those people. I work in order of mag, right? If I say something formed plus or minus 50 million years apart, or 50 million years apart, you can plus or minus another like 50, right? It's not, I can't go out into the ocean and make measurements. I can't go out and do things like that. So I think it sometimes frustrates those people, like the margins we're working on, and the answers I'm trying to get are also within that like times 10 divided by 10 type thing. So even though I'm a geophysicist, I'm actually a hydrologist. And so this is a diagram of the hydrologic cycle, right, on Earth. The ocean, you get evaporation, you get precipitation, it runs off. You have all these things where plants can soak it up, they can transpiration comes from them. There's a bunch of things that are just specific to Earth, like animals and plants. I live down here, but what we're gonna need to think is the things that change. So we no longer have any of those inputs from, anthropomorphic stuff you'd see on Earth, or just things that you only see on terrestrial on Earth. So we're going to zoom in here, and we're going to talk a little bit about each of these things. And so this is the gross interaction between the hydrosphere and the atmosphere, right? Like when you precipitate, then that has two things it can do, right? The first thing it can do is it can infiltrate or run off, right? Like up there is the infiltration part, but it partitions one of two ways, right? And so when I talk about all of my models and I give you rates, I am talking about groundwater recharge rates, which is not precipitation, if you want to think about it. Geomorphologists go the other way. They go from like things that run off only and don't think about the groundwater. So I'm kind of the other side of the coin. The other thing is seepage. Seepage has geomorphic implications. It expresses itself on the surface when these things happen. And so understanding where seepage occurs and how your model fails or doesn't fail, and where those things are is going to be something that's really prominent in this work. So you're going to hear me say seepage a bunch of times. And what I mean is when the groundwater comes up and it starts touching the land and it basically smears out over long distances. It changes the shape of the surface of the groundwater table there. So we're going to think about how we can do this, how it can be a climate constraint. We have that simplified little thing there. But what somebody could tell you is if you removed all that water over there, you would see that up in the mountains, you had these incised river valleys up there that would have been cut, and they had, think whitewater rafting type stuff, right? And then as you get closer to the groundwater table, you start backing up, and you get those sinuous stuff. And then when you hit the groundwater table, which is at the ocean, you dump out and hit a delta. So the geomorph that is controlled, if you much as you think about it from the top, it's controlled by the bottom, right? And so like the landforms you see, as rivers slow down, are produced by where the groundwater table was at. And so people do this on Mars, right? They think about the geomorphology here, and they think about how much it would take to incise all these valleys and like how long it would need to make the crater at Jezreel. And so that's how they get at like estimates of climate on Mars, right? And so I take the flip of it, right? I do the reverse of that. I don't say, okay, I see this thing that got carved by water. I'm gonna make some calculations and talk about how much water it is. I more go from like you carved it. It means that you had place to go. And that can be kind of like illustrated with this just in your head, right? At the Grand Canyon, you cut downward because the water table was lower, right? If you hit the water table, you would back up and form a standing lake inside the Grand Canyon. And then you'd get like, your little clustering deposits. You'd see geomorphology would suggest your groundwater is there. So we know that at the Grand Canyon,
the Constrains?
lake sediment, like you see, there's things called VARBs, like seasonal pumping you can see layers build up, but there's no evidence that like that's there. And so you can say for the formation of the Grand Canyon, it was likely above the groundwater table throughout its formation time. Unless you like recut it all out, but like whatever. In Florida, same thing. You're not going to get a Grand Canyon there because the water table is right there. Like you're never going to carve down that far. And so like I just do the flip of what the geomorphologists do. And so we're going to go through a little bit of Mars water history, just kind of bring you where we're at in the science, right? I like to start with Giovanni Schiaparelli. He's an Italian guy. He named all these really cool things. That's one of his pictures. He was the guy that called them canali, and it was like the wrong word. He meant like canal channels, and it got translated canals, and that's where like this whole like people on Mars thing, where people think about Martians pulling water off the caps and doing farming and all that kind of stuff. Percival Lowell, like the guy that found I was out as a observatory, like he was a huge proponent of like a colonized Mars. Like I think he saw like movements in these canals that could only have been done by like sentient beings. So like they're building up, right? So he's got this popular culture, right? Like Mars, they really wondered like Mars had people on it, right? It's crazy. So H.G. Wells is definitely like real legit sci-fi. Marvin the Martian, like that's where we have him. I just like the thought of like the guy from The Martian, Matt Damon, like showing up and there being like this little donkey-looking whatever thing, like living on Mars. I thought it was great. And then I'm showing my age with the Mars Attacks. Fantastic movie. But in reality, they kind of knew this was coming. Carl Sagan and they were just hoping that maybe like it wasn't dry because they thought about the how cold it could be. They did thermodynamics on the planet and they're like didn't think it could be running water. So they go out there. It's in 65, Mariner flies by, sends back pictures, yep, it's barren and it's super cratered, which means they're not eroding. It means it's retained its like cratering history, right? And so it's kind of dead. They fly there with Viking, they look for life. The search that they used probably killed it if there was it. But they found this desiccated, dried out planet, right? They landed right in the middle of a basaltic field. Not this lush thing where maybe you had canals. But the missions, they give us some more data to work with, other than pictures and a couple sites we land. Started with MGS up in the upper left, Mars Global Survey. We're going to talk a lot about its MOLA data. And then went to Sojourner, which is the first Pathfinder rover before Spirit and Opportunity. That they use that platform for Spirit and Opportunity. MRO is the Mars Reconnaissance Orbiter. That's where HiRISE comes from. MAVEN gives us our volatiles. It tries to tell us about how much water there was on Mars at any point. And then the two rovers, Curiosity and Perseverance. So we're going to go a little bit into Mars though. So using the MGS's MOLA data set, you can now get a topographic map of Mars. Now anything in blue is low, red is high, white's the highest. And you can imagine a world where, imagine on planet Earth, how much could you know about the geology of Earth if you didn't know that the Himalayas were high? And you didn't know that the Marianas Trench was deep, right? So it was kind of like revolutionary to see this when it first came out. And this is mid-90s. And so I'm going to use this, David Carr put this out. It's kind of like a generic timeline for what people kind of think happened on Mars. It's much more complex than that, but this is an overview. It works, and we're going to work through it so we can kind of understand a little bit about Mars. The biggest feature on Mars is this global dichotomy. And so what the global dichotomy is, it's formed way back during these basin-forming impacts you see on the moon, stuff like that. Theory is it was an oblique impact. There's a couple other theories. The consequence of that, though, is that at that scarp there's about a 4 kilometer transition in height on average. Steep, quick, right? It's like 2 miles. And then the crust up there is about half as thick as the crust in what we call the highlands. So it's a dominating feature. And it looks like that in cross-section. So then you can go on to these other two large basins. This is like Oriental on the moon, right? Hellas is the largest impact structure on Mars. It almost broke the planet. Arjar is another one. And they all formed during this time, was 4.1 to 3.7. Keep that time in mind, because that also concurs with this area down here. Now, the bottom period, you can divide the planet of Mars in an upper and a top and a bottom, you can divide Mars's time of water into an on and an off, essentially. And so these things that form, these large things that are forming, all formed at a time when Mars had active water. And we know this because Mars dried out and retained those landforms. These landforms are primarily in the form of what's called valley networks. I call them VNs sometimes. You'll hear me say valley network 50,000 times today. They're all in this train called Noakan train. Cool name is for Noah because it's the oldest train on Mars. And so we're going to focus on that a lot. And when you can see in these valley networks is weakly integrated. This is the best integrated thing on Mars. Integration is kind of like when they make that dendritic pattern, and it takes time to like organize the system to get to like that right? And so when they're integrated, that tells you had sustained hydrology. That's the best. It's like a 6. Most things are weakly integrated. And what they look like aren't these huge dendritic things, but they're these canyons everywhere. They have nick points, waterfalls, and they are huge. They go for tens of thousands of kilometers. The one on the left there is the Grand Canyon. The one on the right there is just a generic valley in Mars. And they're all over the place. And they're not completely consolidated and stuff like that, but they are definitely signs of water. And that's the extent of them in distribution.
Hold on, what are those black dots again?
So each of those are probably a couple. So you can see how this like is sinuous right here. Each black dot is actually a system that there's probably just so many on top of each other it looks like a black dot. But that's the extent of where the valley networks are on the train. And remember, it can only be in trains that are old enough to have them. So some of the stuff, you can see the flat spots and this stuff up here, they're young. They weren't surfaces when these things formed. It's actually, they're probably under there, honestly, to tell you. Okay, and so, there's another place that we're going to focus on, and that's where NASA sends a lot of rovers. And it's because at the time when we had terrestrial weathering, it's in Meridiani Planum. And this is where we think that water touched the surface. We talked about that seepage earlier, right? Like why I'm concerned with this. Here, these are light layer deposits. They're basically sulfate deposits. They think that evaporated, right? But you see all sorts of stuff in Meridiani that tells you the water table was there. And so one thing you see, this is, I think, Spirit. I don't know if it's Oppie or Spirit, but okay, that has to be Oppie. So Oppie lands, another great name for a crater. It lands in this crater, opens up, and they call it Eagle Crater. And why do they call it Eagle Crater? Because they want to see bedrock, and the first thing it sees when it opens up is bedrock, like 15 feet in front of it. And so they called it Eagle Crater because when you golf and you had a hole in one, you get an eagle. And so they named it Eagle Crater. And so what did it see when it unfurled? It saw that. And when it got up close to it, it sees these little things we call blueberries. And these are hematite nodules, and they only form in groundwater. It's like the sign that it was right there. And these are pervasive.
What are those called?
Blueberries. Blueberries, they're like hematite concretions.
Okay.
The blueberries is the colloquial term for them.
What are
Like iron. Iron that was dissolved in the water precipitates out because it gets concentrated enough there. There's the only way you can form that is like precipitation in water. It's like that's why it's a sign of water is because like there's.
Like an earth, sort of?
Yes, you do absolutely. Yeah. You have to have the right pH of water and stuff. I mean, it's a whole like aqueous geochemistry thing on Earth. And so the Spirit of Opportunity was like the greatest rover that ever lived. So it went to this next crater. They called it Endurance because it was going to take like 4 months or 5 months to get there. They got there and they're like looking around like, okay, where do we go? And then they went on to a crater called Victoria Crater that took them like 4 years to drive to. And so like the Endurance Crater was the one they thought was crazy. It was the middle, and then they ended up doing like 14 years. I mean, they learned how to drive rovers backwards. Like they dealt with things breaking, got hit with dirt devils that like cleaned off their solar panels and gave the rover life. It was a super cool mission, but what it showed is a bunch of fluvial features, lake features. The other thing you can see in Meridiani that shows you that water was there is inverted fluvial trains. These are like the insides of rivers that get sinuous, and then you start depositing in them. And then when those deposits turn into rock, they're harder than the rock that was in the fluvial channel. And so what you have now is like a mound. It's inverted. And so you know that was deposited there because it made an inverse mound, not the outcut. So there's a bunch of these fluvial trains that are inverted in Meridiani. I'll show you water tables there for sure. Over here, Spirit had a much harder life. It broke. It landed in a basalt field. They drove it backwards, but one of the fortuitous things that it saw when it was dragging its wheel was this white stuff that's silica. It's opal, amorphous opal, only forms in a higher thermal system. So another sign of groundwater being at the surface, dichotomy. Okay, then we're going to go with Curiosity. Curiosity's sitting at Gale Crater right now. Gale Crater has this like beautiful mound of sediment right up in the middle of it, and they're going through the sediment as a way to look through like strategic column, basically, a strat column. Immediately when it landed, though, it found there's a famous paper called Habitable Fluvial Clustering System. So there's a habitable lake environment, lake lakes in Gale Crater, and you can see there conglomerate rocks. These are like rocks that get turned in rivers and get rounded. The one on the right's Earth, the one on the left's Mars, and just clear signs of like actual fluvial systems. You see imbricated rocks that like lay over with the flow, so you can get flow directions. There's just tons of evidence. Then this leads to Perseverance rover. Percy actually is in Jezero crater because of one of my advisors, Tim Gallagher, could show that this delta was formed in standing water. And because it's different, if you think about Sierra Nevada mountains, right, you get the rain runoff and then you get alluvial fan at the bottom, but that wasn't in a lake. Well, from orbit, it's really hard to tell if it's like that or if it's an actual like thing that built into standing bodies of water. Like the implications of like the habitable environment of a delta versus an alluvial fan are big. And so he could show that that crater, that delta formed in a standing body of water. And he went to NASA and there were 60 teams. He led that team to send it there and it whittled down and they sent it there because of him. And so that's clear signs of water everywhere. This one here is another, I'm probably beating a dead horse at this point. People think that there's oceans, and so people pick these strand lines. I don't really have a preference of one, but like this is a whole cottage industry of like trying to look for, shorelines on Mars.
What's Elysium level?
Elysium. So Elysium is a region. It's that big region up there. I imagine it's when that basin fills. I don't know, like when it partitions off into that basin, like some contour that has to do with Elysium.
For the shorelines too, is there any, like on Earth, the sea level's been, is fairly constant for a long period of time. Is there any indication of how long the sea level was there in order to make these geomorphology features?
You want the punchline right now?
All right, I'll shut up.
Yeah, it affects it. Yeah, of course. Like it's like, I mean, this is a cottage industry too, right? Like people, it's not as simple as you think. The shorelines aren't on equipotential, which is really problematic if you think, because you would need it to be an equipotential surface, right? But when people like back out the formation of Tharsis, and they think the entire planet's spin axis changed. And so like if you back out, like rotating the spin axis, deloading Tharsis, and then like reloading the water, it actually like kind of like works back. So it's like, it's not as simple as like you think. All right, so I showed you all this water stuff, right? But there's still like two schools of, like 50% of people in the Mars community and another 50 like believe in these two different things, right? And that's the warm and wet or the cold and arid Mars. There's like other little hybrid theories too, but like the issue is you have this clear evidence of water, it's like everywhere. But every climate model there is cannot reproduce conditions that would give you that. And so the reasons for this is one's a faint young sun paradox. It also applies to Earth. The sun was like 75% as luminous back then, so your insolation rate was lower. And then Mars also suffers from that 1 over r squared problem, that you get less sunlight the further out you are. And then you can only make an atmosphere so thick before it starts to settle out. It's kind of like you can only dissolve so much carbon dioxide in a soda pop before it like comes out when you open it, right? And so you can only make the atmosphere so thick, its atmosphere actually collapses on itself at its poles at a point, and you're still not warm enough for like surface water. So like how did it have liquid water is like an open question. So I answer that. And like what does that mean for our little Martian and microbes? I mean, this all has habitability implications too. And so can we use groundwater and thinking about where groundwater's at to like think about like what forcings we could put to answer Pete's question? We're gonna try to, but the thing in the modeling community is when you make a model that's complex, you never know. There's small things that can really propagate in a model. And so you try to wanna like bound your problem with like reasonable values, right? So we started with the easiest thing we could do. We thought about these oceans up here that we outlined, and we took the area of the ground, of the land above that black line, and we counted it up in the computer. And then we said, okay, what's the equivalent? Like if I made a perfect sphere and I made a perfect circle at the top of it, what would be the equivalent like latitude of that, right? And so that way we could just say, okay, anything above here, that's our ocean that we think might have been there. Anything down here, all right, that's the high part that I was talking about. Then we can just turn it sideways and go like this, and we would get a pole-to-pole cross-section of the planet, right? We just average it all around one strip, right? So this is just kind of like ballparking our answer. And so I told you it's a 4-kilometer jump, and you can see it go down left to right, right? It's just more pronounced than that because that's like present-day topography. So it's not exactly, though, an on-off function, right? But we're going to treat it like that. And so we can assign a boundary condition, we can do the math, and we can get a solution that's basically a plug and chug. It's a formula. And so, we want to do this for as many possible. I'm going to go a little bit into this, but not into too much. I don't need to know what the Dupuy-Forsheim approximation is. I need you to know what parts of it matter to us, right? What matters is that the conductivity, because we don't know that, right? How fast does it flow like it's in sandstone? Does it flow like it's in a karstic limestone? We don't know, right? And so we're going to think about what values matter for that. And we can adapt this to Mars, so it's our permeability, and we keep density and dynamic viscosity the same, and you can scale it to Mars gravity.
When you say permeability versus hydraulic conductivity?
Permeability is the interconnected of pore spaces. So like shales that have gas in them, they have porosity because they have space for that gas to be, but they have no permeability. They're not connected, so that gas can't get out. And so permeability controls how water flows through something. It's kind of linked to porosity, but not completely, if that makes sense. And so, go ahead.
More like Swiss cheese, or?
I mean, I'll make an argument about that. Like, that our Swiss cheese karstic rock out here, I'll give you an idea of like where that rates on what I use, and it kind of gets your mind into it because like it scales it in a way that's meaningful. Recharge is where and how much I put my recharge. Remember, that's recharge, not rain. It's minus the runoff, right? And so out of this thing, when we did this dimensional analysis in this really easy way, it pops this value. This is the recharge divided by the conductivity. It's a unitless number. This number I thought was meaningless, and my advisor told me to put in my first paper, and I did, and like I'm so glad he did now, and you'll find out for reasons. So these are just the different equations we can use. This is actually one condition because we moved the shoreline and everything, but it's literally a plug and play. And from that, what we did is we wanted to know how sensitive is this problem. That's just a little toy math problem we have. How sensitive is it to where your shoreline's at? And so what you have here is that same cross section. The recharges that I supply the model, or the analytic solution here, are those. And then you can see that vertical black line, that's where I'm basing those shorelines are, moving it around. Punchline of all this, I divided by 10 times 10 is my standard, right? Those things are not divided by 10 or times 10 in magnitude compared to each other. Like literally where your shoreline at does not give you a times 10 or divided by 10 effect on your system, which is, I'm in my bounds, right? The other thing is we want to think about where we put the ring. And so starting at the top, if you go pole to pole and you equally recharge your aquifer everywhere, that's about maxed out, right? You almost hit that times 10 with that one, but that's kind of ridiculous to think that you would go pole to pole and be recharging your whole planet. And so we're still pretty much within that times 10 or divided by 10. And so what we want to do now is we want to go a little more complex. So we use that approximation. The issue with this approximation is that's the divergence of your head. Your head is your groundwater table elevation. I'll say head all the time. It's a hydrologic term. It just means where the top of your groundwater table is at. So it's the divergence of your head, h, times the divergence of the gradient of your head. That means it's a nonlinear problem. You can think of it as like x squared plus y squared equals 1. There's all sorts of combinations of x's and y's that I can get you to 1 with that, right? So that doesn't have a single answer. And so that problem doesn't have a single answer. It makes it nonlinear. So we need a Newton-Raphson solver that kind of like jiggles the solution. It'll know something about that first solution, change it a little bit, and then kind of like jiggle it until it stops changing. And that way it kind of like finds that nonlinearity that best answers your system. It's a numeric thing you got to do. Spherical shell coordinates, this is easy, there's a fancy name, easy concept. When you're on a plane, you have those grand circles, supposed to rhumb lines. And so when you're on something that in that geometry, you need your math operators to work in that geometry. Otherwise, like if you ran on a straight line, it would be a longer length than that circle, right, when you're on a plane. And so that your math works correctly, it's in that geometry. Harmonic boundary conditions, and another thing is just makes sense. It's where your planet wraps around on each other. Like when you go across the international date line on Earth, you end up on the other side of the map. And so you have to make these solutions talk to each other, and then you have to map everything back to a pole. So that took the better part of a couple of years. But what it made us be able to do now is, this is the improvement of my model compared to the previous work before me, is I can tell you there's a topographic boundary there, and if I think that that's a lake, I can identify it. And I can identify the cells on the inside, I can identify the cells on the outside, and just identify the cells on the boundary.
Is that Hellas?
Yeah, that's Hellas.
Okay.
So I just found an arbitrary contour. I'm saying if I believe my groundwater is there, this is the shoreline. And so then what I can do is I can take and pull all those cells out because they're just in my water body, right? Like the groundwater is just right there. And then I can assign that as a boundary condition to my model. And so in doing that, I'm enforcing an equipotential surface. Like you think of the ocean as just a solid surface, right? Well, I don't need to model the solid surface. I just say it's a solid surface across that whole thing. And by doing that, I can actually accommodate like standing bodies of water. And people haven't been able to do that before. And it's done like that, looks like that. All right, and so these are my first paper. What we're looking at here is that map of Mars. We got the Arabia shoreline. What I've done now is I calculated the groundwater table level, and then I subtract it from the topography. And so anywhere my groundwater table is at topography or above, it's blue. Anywhere else it's not, it's red. White is like where it's right at it, right? And so what I did in this one is I said, okay, we're gonna recharge for 0.01 millimeters a year, but we're gonna do it all year. We're gonna take this value, okay, my conductivity is 10 to the negative 7, we can talk a little bit about that. And we're gonna band it on a band from 45 north to 45 south. And when I calculate that surface and subtract it from topography, this is what you get. And what this is showing me is you kind of get a little bit of water surface where you expect it to. Remember right in that middle of that place where I showed you all of those things were, that the rovers were finding. And there's no water breaching here. So we can now play this game that modelers do. I say, okay, well, let's raise it. Let's see what we can raise it to. Raise it to 0.03. Now you see much more interaction with the surface, right? That groundwater table in the middle there is breaching the surface, but it's still not in the places where you see the valleys being cut. So that's generally okay. Let's move on. Last one, 0.1, you're blowing out the whole planet. And that's 0.1 compared to 0.03. And so the jump is very fast on Mars. And you don't see the geomorph that suggests that. And so that was the punchline of my first paper. What we did is on the y-axis you have percent of the highlands that they're experiencing being in contact with groundwater, and on the bottom you have log scale of recharge millimeters per year. We went through all the literature, and these people who look at how long it takes to cut valleys gave that range that's there in the blue. The people who do like basal melting of like glaciers and stuff is the lighter blue, and then the modeling work that's out there is in the brown. And all of those three I showed you are in those panels there. We'll bring them back to remind you. They're all down there. And so like, what is that? Like, even the bottom part of that modeling one there in the brown line, that's the person who did work before me, and he couldn't have an ocean. And his number was 10 microns and mine was 30. And so it's like another confirmation that like where your ocean's at doesn't matter on Mars. It's interesting. So he did like the no ocean version. So, you know, that dimensionless number matters. Is what we got out of that. And where it's going to come, at least we thought it mattered in the steady state. There's a few implications. This maybe Mars didn't have a lot of water. Maybe it couldn't, you know, once you got out of whatever climate forcings there was no active water left to evaporate. Who knows? What I'm going to explore now in this, though, is the transient response. And what that is, say you have a water table that's way down there, and you start recharging it, that water table will go up. But what happens is before you breach the surface and start making signs of geomorph that I don't see, you turn off your water, and that water table recedes. And so what are the time scales that takes, and what are permissible, and what does that say, you know, compared to other stuff that's out there? And so we take our problem and then we expand it this time to this. This is actually in the PDF form, or PDE form. But I want to focus not on the math, but on the things I need. These are new compared to our old problem, right? So that our conductivity now is variable. There's that S term and H term, but the first thing you need, though, is it needs to be transient. So we have to be able to change in, that's change in head over change in time. So we had that term. Storativity. This is a fancy hydrology word for something we all get. As you go down on the ground, the pores of the rock become smaller and less connected. And so if I poured water into the bottom of the ground, not a lot of water, it wouldn't take a lot of water to raise the level because like, there's not a lot of space for that water to go. But as you get towards the top, there's a ton of space for that water to go. So it takes much more water to raise the water level the same amount as it would down there, right? So I have to have a term that accounts for how my aquifer responds to a certain amount of water, depending on where it's at. And then go back?
Yeah, I want to see that graph again.
So those are two different models, the way of doing it. I do power law. It's not too much different. We try them all. Megaregolith is one that like Andrew's Hand does. He was my predecessor, the one I talk about a lot. There's just I don't know if I buy, it's like Planetary Science. Do I buy them? No. Do people use them? Yes. You don't know what the conductivity on Mars is or how it's, you know. So anyway, these terms right here include these. And so in a model 2, we also have a permeability decay with depth. And what that means is if it's moving, it moves much slower because remember we squeezed the passageway between the pore cells, so water can't go as fast. And so if your aquifer is really low, it doesn't go as fast as a full aquifer that will go fast with where it's still at the top and has all the pore spaces it can access. And so I have to be able to change my model when it does these things. And so I have this model. It's kind of cool. It's my first work. You can see I do a centimeter a year. and then you can see it waning off. Now it's off, and it goes away, and it's going to pop back up again with another, like I think 12,000 years at 250. So cool, that was my first time I ever did it. One thing that doesn't work on this is the shorelines aren't moving. So if you're moving water around in a system, you have to maintain some type of mass balance, right? Like, so that's the next thing we got to do. I guess that's weird. Okay. All right, so I have to move the shorelines, right? And so at the first one, we have it in the right? It's a higher shore. And then in the next step, it comes out. And so what that is basically simulating is a cold trap. So basically you got cold, any maybe water you had up on the top turned into a glacier. So you've trapped some amount of cold, and that's during the off times. You would presume that during a glacial or during a glaciation event, you would not have much recharge precipitation, stuff like that. And then it goes back out to Arabia when it's warm. That becomes computationally a problem because remember I told you I turned those cells off? Well, now I got to turn back on. And like, what do you give them values of? I just go with the topography, which is like that. And then if it intersected topography, I would just give it the value of the old ocean. And then you would allow your shoreline to go ahead and evolve again. It made all sorts of numeric problems though. And so another improvement off the old papers, I would just use the top of the water table. I wanted to get a little more exact. I took Dr. Gouge's valley network information. The top is the where it's at on the land, like whether it's at 1,000 meters or if it's down here. And then it's density. So I wanted to be able to compare like how dense these structures were. So if I said 50% of my cells with valley networks are flooded, well, then maybe they have 75% of all valley networks. It's like much more important if certain places are flooded, right? So I weight the place it's flooded, and wow, I tell whether it's flooded is off the middle point of the channel. So all those channels I have files on how deep they are, where they're at topography-wise. So I just pick an elevation right in the middle of them.
Hold on a second. So the map above that shoreline you're saying is that's likely during a glacial event because there's the shoreline, the highlands dominate. Yeah,
the shoreline recedes. You would have you'd have glacial processes all up in the highlands.
And so the bottom one is whenever there are no.
The bottom shoreline, yes. And then we
glacial storage.
Yeah, we mask all this too because you do get glacial stuff above and below 45. And so like we don't want to like think about those processes altering the processes like we're thinking about. And so now what we're going to do though is to make this model transient, we also need to think about recharge. I scale it towards the equator because that's where downhill is. And that's where even if it didn't rain there, it's going to infiltrate more there. And so it's basically on a sine function on the equator. And then I just plop it off and on and off and on. And this is from 1D work I did. We're hoping to get to something like this where you can say, if you rain for this long and at this rate, then to stay stay okay with the geomorphology, you got to go into one of these time belts. So you can get a value, and that value, go up and find. And if that value is in here, you need to stay off for 10 million years to not break the geomorphology. That's the goal. So we need to be able to look at the parameters. We need to be able to think about what combinations of rates, right? And so I do that. Well, I was going to show you. I don't know if this is going to work. Yeah, I don't think it's working. Yeah, it's a video. So it's boring, right? Once it hits steady state, the oscillations of the transient, like the transient will get to a certain spot and just sit there and vibrate. It's a nothing video. So it's just as easy to show you stills, but know that they're transient in time. And so what we see here now is 500 year recharge event, 1,000,000 years off, and then we give it a pulse of recharge on that band, and you can see how much the valley networks were flooded. That 20 down there, I would think that most people could agree with that number. And then if you go to 650, I don't think 60% of the valley networks were ever flooded out. I don't think most people agree with that. And so the interesting thing about that is that R bar, that K bar number, the R over K, those are still sitting right at that number that came out in my first paper. So that means that I can spread the rain out over all of geologic time to get this answer. Then I can also add the rain up in certain combinations. It's all still governed by this one non-dimensional number, and that has to do with the geometry of the planet. So this is super, super useful. There's another. I thought these were neat because they're the values and like how the values can change with the times are definitely different. And then like as you get more time in between, you really get these cool oscillations. It's as you pump a ton of water in there and then it slowly drains away and you pump a ton of water. When I show you the answers coming from all these things, I take the average of this because the averages are all the same. And so that's that number. So what we did is we ran a bunch of sweeps. I did a zillion simulations where that RAV is the recharge rate, the interval is how long it was on, and the quiescent interval is how long it was off. And you just divide by this. The thing I was telling you about conductivity, it's a scalar. And so if you want more conductivity to get you more recharge, at some point it gets ridiculous. Like to get another order of magnitude on Mars, you would have to make karstic limestone all the way down 10,000 meters. And so like it's not realistic. And so it does act as like a governor. So even though we don't know, it's just a scalar. And so then I ran all these runs and made sure it hit that number. And here's the results. That no matter these combinations and all these things I did, when I divide it all out for that, I calculate the R bar over K bar and I calculate how much of those value networks are flooded out. It don't matter how I chop it up. At that ratio, it floods like that. You can see down there that 10 to the negative fifth. At 20, I told you people probably accept. Everything's above 10 to the negative fifth. So this is like a powerful tool to look at these things people do and say, oh, it had to have rained this much and this long and you know, had this much work done to it in order to happen, because I can put a limit on whether that's plausible or not. So R over K is useful. Wet and warm, cold and arid is probably not as simple. We're gonna get a little bit into that for a second. Mars groundwater system is likely detached. And you know, we're thinking about how we figure these things out. I'm gonna show you,
What do you mean by detached?
well, I'm gonna get into it in a second. And so like this, great science is not like they're wrong and I'm right. Like the people who do all the geomorph stuff, they're probably right too. It's like, how's that possible? And so like that's where my work's going. So I told Pete I'd give you a little bit more stuff on where it's going. I'm submitting work soon once my dissertation's up. Next thing I'm gonna do is I want to speed my model up and I want to make craters. I'm just thinking, sitting there like, okay, there's a lake in my crater. That's equilibrium, right? Well, what happened when the crater formed? Like Hellas would stretch from Washington, D.C. to Oklahoma. It's twice as deep as the Grand Canyon. It probably has 15 kilometers of like newly created space under it that has pores and stuff. Like all the oceans are draining into it. How long does that take to fill back up? And so now I need to calculate all these shorelines so my models can bring it in. You have to do a whole bunch of stuff on telling water which way it goes, because negative signs is like a direction. So you have to be able to add it right. And then thinking about how these shorelines move as you fill things up. And so the top one is this really cool idea. If you, like on Earth, we think like, you know, something happens that makes it warmer, we get like, you know, transgressing seas and it gets colder, we do regressing. When this happens, you have a big shoreline, say you have a big shoreline in the Northern Ocean. As Hellas fills and fills up all that pore space, the shoreline of Hellas is transgressing while the shoreline of the ocean in the north is regressing. So you like have this like teeter-totter system set up, which is just something that we don't think about on Earth, because like you know, when does that happen? So yeah, and so the thought of that is, I don't think it's gonna play this. Yeah, that's okay. It's just thinking about how much space you can make under a crater. There's work's been done on that. And then thinking about how like life moves. The other thing I'm going to do is look at like groundwater systems and crater rims and see how you cut into these things. I'm basically thinking if groundwater would be the force that you would need to cut crater rims. Yeah, I guess it is. And the last part's the seepage. Oh, of course I did. I have a bunch of experiments I'm thinking about, like how to include seepage and not blow up my model. Because part of my work was just making sure my model worked properly. I've told you about the laboratory analogs. But now we're thinking about like how can we include this thing that's obviously very important on Mars. And because what I think happened on Mars, none of our numbers line up with any of anyone else's numbers. Our numbers are like sub-Atacama desert numbers. I mean, they're wild. I mean, Atacama can get up to 250, I think, millimeters a year, and we're talking, you know, 500 years of like 10 millimeters, like that kind of stuff. It's like dry. And so like they don't really add up. And the only thing I can think that maybe would make them add up is thinking about if you had a groundwater table that was just dumping into the bottom, a drain got pulled out where that big crater formed, and then you never interact. And so I don't have to worry about filling it up because all the water is just going down. So you can rain all you want without making it expression on the ground, because like the groundwater table is just completely disconnected from the surface water, because if it wasn't, you would flood everything out. And so like my next paper will be working on like thinking about how long those processes take and what are the implications for a planet that like has decoupled, you know, groundwater systems from surface waters.
The green, is that the region that had the channels?
Up here.
Yeah.
Yeah. This is.
Okay. And so the logic could be too then, as Hellas fills up, that area would be dried out. It was once underwater, and now it would not be underwater as Hellas fills up.
Yes.
And would that drainage, so to speak, so the regression, would it be possible to make the geomorphology features, the channels and such during that process?
Not where they're at, no. You see some at the bottom of it. It's like when I put those circles, like there was a part that was missing. Well, you'd see parts that were missing in the map. It's like a bowl. It's basically like there's a rim on it that still scours, but inside that bowl you get all those inverted fluvial trains, and so like there's still scouring on the back side of it too. So like I don't think so. I'm not a geomorphologist, but like that's not what I think is.
So you don't think that your idea of filling out Pellis is responsible?
I think it could be. I think it could be. I think that's another thing is like when is this happening? Because the light layer deposits actually are behind temporally the valley network events, and think what gives that gap. Like there's also sort of like chemical issues with the light layer deposits because of the water chemistry you need and how long the water could sit in the rocks, and so there's a discrepancy with that too. So it's obviously like something going on that's like not well understood. And like, could it be a fluctuating table as these global systems? Maybe? I mean, they think it's a fluctuating table, but is it, in response to the recoupling of the hydrosphere? Because like that would be the first place it happens. It's the biggest transition. Like it's at scarp. So like right at that big scarp, that would be the first place that would start intersecting.
And so in this last picture then, that's the shoreline, not in Pellis.
The left one?
No, the one with the green. Okay. So where would the scarp would be roughly where that?
Yeah. Right. Yep.
Okay.
Yep. And I mean, there's also like thoughts about what if that's really happened. Like, would you get transgressive ravines? I don't think people think there was really like geologically standing bodies of water like, anymore. I'm in the cold and arid camp now. I started in the warm and wet, and I just don't see how it's possible. But I mean, there's ways to constrain the climate and once you start constraining the climate, then you can get at drivers and thinking about like what could produce it. Like what your precession on Mars is hard because it's like doesn't have a big moon to hold its precession. So like there's times where it's rolling around on its side, and is the insolation rate all on the top part of the planet? Is that enough to like, move snow up to like glaciers and deposit it so you get like who knows? Like I don't. You have like impact structures that are going on that are aerosolizing things. You have these big volcanic provinces. So who knows like what combination of these things and what rates people think they're capable of putting out would line up just right to like overcome the issues with the model, like the global climate models.
So this is about billions of years ago?
Yes. It's a very short period of time too. It's like 300 million years.
So why are we interested? Is this something that says, there could be groundwater trapped somewhere for our use if we colonized?
Yeah, so good question. Yes, there's a habitability implications of it for that side. But I think, and I've thought about this, is that you probably have, people model groundwater and they model a flat bottom aquifer, right? When you create these things, the bottom of your aquifer is not flat anymore. Well, everybody models it that way because that's like the easiest thing to do that keeps it in a computer that like I don't have to pay for time at taxi. But that undulation of the ground of the bottom of the aquifer, because basically you hit what's called brittle ductile closure, your material properties become so much that like any pore space collapses. So you have a bottom down there somewhere. But this being sloped, like is there a depression where you get brines? Maybe, I don't know. Like where's the bottom? I think it's interesting. I think it's interesting too in thinking about like as these systems evolved, where would the most flux been? So if you want to go find signs of life, they say look for the water, and the water's had water-rock interactions that give it the chemicals it needs, it gives it the gradients it needs. Like what rock had the most water flow through it? And like going there and drilling. I'm saying like, what plausibility you might have lithospheric rock down there, or lithospheric life that's eating.
So like microfossils?
Yeah, or it wouldn't shock me if there's like methanogens on Mars. It's anecdotal, and they get methane bursts. It could be geologic too, but like it wouldn't shock me. This is right at the time. It's interesting. This whole thing's interesting because I wanted background gradients because if you think about like why did life start on Earth, like mid-ocean spreading centers weren't a thing back when life started, like Archean, right? And so you didn't have plate tectonics hadn't started at the time. So why did you get life? Well, this is the same time life started on Earth as this time on Mars. And so I've always had this pet thought that maybe you could have spatial and time scales where you dig out one hole and you can move water from one crater to another crater because post-impact hydrothermal systems are analogous to mid-ocean ridge spreading centers. So it wouldn't shock me that a planet that had water running on it, that had pH of Earth, that had temperatures of Earth, and was experiencing the same thing as Earth was going through, it wouldn't shock me if there was life, some exit life there. I mean, there's this whole co-eval idea, now Cabral puts out, that I like too. So as Earth got life, Earth changed, and the erosional rates changed due to the oxygenation. All these things, the whole Earth system changed. Vegetation stabilized bank systems, so tributaries changed. All these things change when life comes. Well, on Mars, it's a story of losing your water. So if life has to adapt to the change in the planet because you co-evolve, the only place for life on Mars would have been underground, where it's protected from UV, where the partial pressures are enough to have water, stuff like that. And so, anyway.
So we're not going to find microfossils at the surface. We've got to drill for them.
Maybe drill what we do.
When water moves through an aquifer, it's driven by gravity. But Mars has less gravity. Does that affect the rate of flow given a certain gradient? And does your model need to take that into account?
It absolutely does, and we do. So yeah, when I was talking about permeability, how close how connected it is, porosity is a term in there, and we just keep the other two changed. The permeability is what we use along with gravity. Gravity is what we change, right? We look at permeability and make it curve, but we alter the conductivity's gravity by literally inputting Mars's gravity in the term. It essentially slows down flow. Given the same material, the same height differences, it slows it down because gravity doesn't pull it as hard to go through the rock. They pay me to do this.